My name is Damon Cortesi. I'm going to be talking today about Airbnb's Spark on Kubernetes journey. So quick bit about me. I'm a staff software eng at Airbnb. I've been working on data platforms since about 2010. I had a startup back then. We were doing MongoDB, migrated to HBase, so lots of good fun back then. I've been a stats nerd since 1996 when I was doing automated data entry into Excel, so clearly I choose all the right technologies. I'm also an open source contributor. I'm an Apache Libby committer. I opened my first PR on the OpenTelemetry project this year. And if you go to my GitHub, I got a bunch of fun tools there too, like a Rust-based S3 grepper that does it all in parallel. Because it turns out I looked through a lot of logs on S3. So let's get started. So why Spark on Kubernetes, right? Let's dig into this a little bit. We've had Hadoop for nearly 2 decades now. It's still being actively developed, right? But things like Java support, for example, are a little bit lagging. I think Java 11 runtime support was just introduced in 2022. So why Kubernetes might be obvious to everybody here, but a few specific reasons. One is flexibility. So Spark versions, right? For us to be able to upgrade a Spark version in our existing cluster, it's kind of challenging, right? Hadoop 3 does support running both Docker and Run C containers, but Kubernetes is a much more mature solution for that. The second one is compute optimization. This kind of goes along with flexibility. So we've done a lot of work optimizing our existing clusters, but it's not as automated as we'd like from an instance type perspective, right? We have to do a lot of picking and choosing and kind of figuring out what the right instance type is for our workloads. And there are options like Carpenter and Kubernetes that are a lot better for that. So we use internally Carpenter as our autoscaler, and that's responded really well in early testing. Finally, we should be able to have more efficient resource utilization in theory if we have shared workloads on the Kubernetes cluster. With Spark workloads, though, they can be pretty bursty. It's not unusual for us to spike up to, from 5 or 10,000 running in pending pods up to 30 or 40,000 running in pending pods. So we'll see if this one actually holds true. Next up is modernization. So like I mentioned, Hadoop, Java runtime support, still a little bit challenging. With our existing Spark clusters, upgrades are a bit challenging. We do have a really good framework internally for rotating the clusters without any sort of user impact. But if we want to upgrade something, it's still very much a lift and shift approach. Kubernetes allows us to more easily update parts of our workload. You can just drop a new Spark version onto a new container image and test it out on the same cluster without doing a ton of work. So that's one thing that's really, really nice. Observability for us is much better in Kubernetes as well. We use OpenTelemetry internally for our metrics collection, and we have a lot of paved pathways internally where some of the observability things are more baked in on Kubernetes than our existing solution. Finally, we have the opportunity to make the developer experience a lot better as well. I used to be a former developer advocate, so this one is near and dear to my heart. But if we build this with our users in mind and also with all the AI systems out there in mind, we can do a much better job of providing what our users need and help make them happier on a day-to-day basis. Industry adoption, right? Kubernetes in general. More organizations like us are adopting Kubernetes and also adopting Spark on Kubernetes. So just the general trends in the industry are pointing this way. And then even in open source, right? The most recent Spark release, 4.0, it had over 300 Kubernetes-related JIRAs merged. That is a pretty insane amount of innovation there in Kubernetes in Spark. So that's one thing that's really pushed us over the edge. To level set a little bit, let's talk about Spark at Airbnb. Show me the numbers. This is P90 stats from a week of our existing environment. So at any given time, we've got about a petabyte of memory provisioned for our Spark workloads. Of that, we're about 88% utilized, which from what I've seen around the industry is a pretty good utilization number. At any given time, we've got about 87,000 running Yarn containers. These are just the Spark drivers and the Spark executors, right? So this is across our entire workload. We've got almost 90,000 containers running at any given time. And then every day, we run somewhere between 700,000 and 900,000 jobs across the cluster. So pretty decent scale. And as we're moving this over, trying to make sure that we do it in a way that is efficient, especially from that resource utilization point of view. I want to make sure we kind of keep those numbers high. Our environment, for various reasons, we're running a slightly older version of Spark 3.1.1. Most of our workloads are Spark SQL, some Spark Scala, and some PySpark in there. We also have various internal frameworks that people can use to easily build their workloads and deploy them into our environments. So we do have some internal abstractions that make some of the migration easier. One thing I will caution is that Like I said in the earlier slide, a lot of Kubernetes support has been added to Spark even in just the past year. Our version is over 4 years old, and there's little tricky things that might catch you that you're not expecting. One simple example is the Fabric 8 client in Spark 3.1.1, the Kubernetes client. It does not support rotation of long-lived service account tokens. So if you want to be able to have service account token rotation in your cluster, we had to backport that patch in order to make that work in our clusters. So there's a lot of little tricky things like that where you look at it. Another one that we ran into is when Spark Submit runs, it actually does a list watch on every Spark Submit. Not great for our clusters, so we backported a patch that actually fixed that as well. What else we've done this year? We've also deprecated Hive. We're on the tail end of an Iceberg migration. We've also just recently migrated all of our Spark jobs from client mode to cluster mode. And a lot of this is thanks to the Spark submission service that we've also put into play as well. So I mention these because all of these things are kind of setting us up for success in the Spark on Kubernetes migration. If we had to deal with people running Spark submits on their laptops or on random gateway nodes, it'd be a lot harder. But we have a central submission service now that controls a lot of that. The Iceberg storage story is also something that's important. If you've ever tried to figure out which Hadoop S3 library to use, you might just walk down the street and cry yourself to sleep or something like that. So using Iceberg makes that a lot easier. So where are we on our Kubernetes journey? Well, as of this month, we've migrated about 38% of our production workload onto Kubernetes. Now, I really like this number not because it's so big, but because a month ago, this was 1%. So we started this project over a year ago, so that raises two questions, right? Like, what have we been doing the past year? And B, how did that number jump from 1 to 38% in the span of a month, right? So we'll talk about that. And then there's three big buckets that we've largely been working on. One is internal integrations. So we want to make this transition as seamless as possible for our users. If we do this right, nobody in our company should actually notice that we've migrated to Kubernetes, except for maybe our cost folks that see a really nice lower bill, right? Everything's going to be cheaper. The other thing is decision tree complexity. Every step along the path where we've migrated, we've found something that existed natively on Hadoop or Yarn, but doesn't in Kubernetes, at least not natively. And with Kubernetes, there are multiple options. So every time we face something, we'd have to pause, evaluate all the options, from a licensing perspective, from a compatibility perspective, all that kind of stuff, and figure out, is this the right one for us? And then 3, validation. Not like self-validation, but we just wanted to make sure that this was the right choice for us, from a cost perspective, from a performance perspective, and then from a human perspective as well, right? We've got a lot of folks that have been working on Hadoop for a while. Like I said, I used to do H-based stuff a long time ago and still have the lack of hair to prove for it. But is this the right choice for us to move to Kubernetes as a platform? So today I'll mostly be talking about point 2, the decision tree complexity. All right, the journey. So this is the decision tree complexity I was talking about. It's a little hard to see. I should have made some of the texts bigger, but the slides are online. But essentially it's showing that at every step along the way, it's like a multiple choice problem, right? Even just getting onto the Kubernetes cluster, right? Are we going to do it with Helm, or are we going to do it with Argo or Flux? And there's a lot of choices here. These are the decisions we made. It's not the choices you will necessarily make. Every organization is different, of course. But as you step through it, there's a lot of things where like, hey, that was built into Yarn and built into Hadoop. Things like queues, right? That's built into Yarn. Preemption is built into there. There's this thing called a native shuffle service that just runs in the background. Turns out it's a pretty important thing. Logs go to HDFS, and with Spark, you get a history server that's running there, tightly integrated with the Hadoop ecosystem as well. Some things on Yarn, like little driver links in the Spark UI, don't exist in Kubernetes. They're just not there. So there's little things like that, too, that are surprises along the way. What I want to do is walk you through these, talk through how we made some of these decisions. The boxes with the colors, those are the ones I'm going to mostly focus on. Quick spoiler, on the right-hand side, there's the scheduling system. We use Unicorn as our scheduler. So it's got a lot of the functionality that we needed from Yarn, and that's been working pretty well for us so far. Let's see, anything else I need to call out there? I don't think so. But yeah, let's get into it. All right, so Spark job submission. Pretty simple, right? Spark submit, -- master Kates. You're done. Not quite. Couple important things to call out. Spark jobs are not Kubernetes capital J jobs, right? You would think if you've got a batch job, you might run it as the job resource in Kubernetes, but Spark, of course, doesn't do this. What it does instead is when you run that Spark submit, it's creating the driver pod spec for you and submitting that to the Kubernetes cluster. So it's essentially just doing a kubectl apply, right? The interesting thing about the Spark driver is it also needs permission to create the pods. So the Spark driver is actually taking care of creating all the pods for you and deleting all the pods for you. So that Spark driver needs a special set of permissions. And that makes things a little bit tricky from a security perspective as well. I feel like that's slightly different than the way most things do it on Kubernetes. So that was something that we had to kind of work through. So yeah, when you run that Spark submit, submits that directly to the cluster, so you probably don't want your users running Spark submit with create pod permissions on your cluster. I don't think most folks in here allow their end users to do that. So there's a couple options. There are two operators out there. There is the kubeflow operator. This was originally from Google Cloud, and it moved to the kubeflow operation at the beginning of last year. When we started this in 2024, there was not an Apache operator, but there is now. So things change a lot. But a couple of the differences, the kubeflow one is Go-based, like many operators. The Apache one is Java. All right, cool. Kubeflow's been around for a while, has a really large community. Apache one, the first release was in the middle of last year, I think the summer of last year. They did their first 1.0 release, I think in May of this year. The Apache one's really fast. It's just using the Spark libraries to do Spark submits. So it's calling the submit driver directly from within the Java code. The Go-based one actually forks a JVM Spark submit process for every job that you submit to it. So if you're running the kubeflow operator on a single pod, which most people are, you're going to find really quickly that JVMs take up a lot of CPU and memory, and you're going to slow down pretty quickly. Let's see. One other thing we ran into with the Apache operator, the Prometheus metrics come out flattened, unfortunately, which makes, if you're using labels or anything like that, makes querying them pretty difficult. There's ways around it, of course, but again, out of the box, it was kind of challenging. It does have some cool Spark cluster support, though. So Spark cluster is it's a long-standing Spark concept where you essentially have a standalone cluster. It was mostly used for like local development in the past, but a lot of effort has gone into making this run on Kubernetes. So it actually creates kind of a virtual cluster for you in Kubernetes. It uses stateful sets for scaling. It has its own UI and everything like that. It actually works pretty well. We did not, unfortunately, make use of that Spark cluster support, but maybe we'll revisit it again. So let's see. How about we do a little audience participation, make sure we're awake. Who thinks we use the kubeflow operator? Raise your hands, please. All right, we got a few. What about the Apache operator? Who thinks we use the Apache operator? Better be everybody else in the room. That's about, it's about a 50-50. The answer is neither, so. We already had a job submission service, right? We've got this central Spark submission service, and what we found was adding the operators just made it harder. Our Spark submission service generates an ID. The Apache operator generates its own ID, but it also appends an incremental retry integer to the end of that ID, so that makes it even harder to kind of trace your Spark apps all the way through. That specific bug, I think, not a bug, that specific feature has since been changed in the Apache operator, but we already kind of passed that. So we have the Spark submission service. We've got a Kubernetes cluster now. We've got a namespace. We can submit drivers to it. We'll probably revisit the operator discussion at some point down the road, but right now this is kind of what we look like. All right, so we can submit jobs to Kubernetes. Yay, that was easy. That only took a couple months. Let's talk about the shuffle service now. So shuffle on Kubernetes isn't as easy as Hadoop, particularly if you want to use something called dynamic resource allocation in Spark. This is a great feature that allows Spark to scale its workloads up and down depending on how many tasks there are. Unfortunately, there's a service called the shuffle service required for this that doesn't exist natively on Kubernetes and just magically exists in Hadoop. If you do want to use DRA in Kubernetes, you have to enable something called shuffle tracking. Shuffle tracking is nice. It allows you to use this dynamic resource allocation. The downside is if there is data on an executor that's needed somewhere down the line, Spark keeps that executor around even if it's not doing anything. So from an efficiency point of view, it's not great. So you can either enable shuffle tracking, or you can look into one of the many different remote shuffle service options that are out there. So another decision point, right? Let's sit down, let's do an evaluation for, this will probably only take a few minutes, right? But there's a lot out there, so we can do shuffle tracking, native shuffle tracking. There was one from Uber. They had an Uber RSS. That seems to be no longer maintained. AWS has the Cloud Shuffle plugin that uses S3 for its shuffle data. That wasn't quite performant enough for us. So the two options left on the table are Kelleborn and Unifil. They both have really good communities. They're both kind of about the same place. Kelleborn had better documentation, so when we got into it and we were spinning it up and using it, they had really great docs that we could reference. I will warn, though, similar to Spark, there's like 1,000 different configuration options for Kelleborn. So make sure you spend a lot of time just reading through each and every one. With Unifil, the documentation wasn't as great. When we were spinning it up, we found we had to look into the source code more often than not to figure out how to configure it. So it wasn't as easy to get up and running. And Kelleborn ultimately won out because it also has the best support for our wonderful Spark 3.1.1 version. So we went with Kelleborn. One of the other things that we did during this process as well was benchmarking, of course. So we used primarily the TPC-DS benchmark, the 3 terabyte scale one. So the baseline, the blue line at the bottom there, the 0% all the way across, that's the test run in our existing Spark clusters. We also ran the test on just our stock Kubernetes environment, and that's the red line down at the bottom, or sorry, that's the yellow line. And then the red line down at the bottom is when we ran it with NVMe disks under the hood. So this is pretty straightforward. It shouldn't be a surprise to anybody, but it turns out the yellow peaky lines there are TPC-DS queries that are shuffle heavy. They're disk heavy. Obviously, if you're running an EBS, a GP2 EBS disk under the hood, that's going to be slow, right? The TLDR here is that make sure your disks are optimized. But you can see, for pretty much every other query, Spark on Kubernetes performed better. We were using the same version. We were using mostly the same instance type, so we didn't change a lot there. So we were pretty pleased with these benchmark results. All right, so now we have a shuffle service in the cluster too. And one thing you might note about this, obviously these are very simplified diagrams. Sorry, I couldn't find my graphic designer. But we are running Kelleborn in the same cluster as Spark. Some people do this, some people don't. The reason that we did it, it was kind of easier to get up and running, and we could also use cluster local DNS when addressing the Kelleborn environment. Kelleborn uses stateful sets, and the Spark executors connect directly to each of the Kelleborn workers. So this was something that just made it easier to kind of get up and running. We'll probably revisit this in the future as we scale it up, but being able to deploy kind of an isolated cluster with both Kelleborn and Spark workloads on it was just a little bit easier. All right, observability, logs everywhere. So there's 3 different components when it comes to observability on Spark. We've got the Spark UI, and that is, Spark provides a UI for both running and completed jobs. Of course, it's a little tricky because the running UI runs on the driver pod when you run the Spark driver. So the Spark driver spins up, exposes a local port, and you can connect to that local port. We're probably not going to give everybody port forward access to the Spark drivers, and we don't really want to register those drivers on the mesh every single time a job comes up and down, right? If we're running 700,000 jobs a day, we don't really want that workload on our mesh cluster. For completed jobs, it's entirely different. When Spark's running, it writes out this event-based JSON file that basically tells or says what every single thing that happened during the Spark job was. And when it's done, it uploads that somewhere, and the Spark history server loads that event log back in and reconstructs the state of the entire Spark job. So awesome and fantastic. But we needed a way to make that separate service available as well. For container logs, these are just the raw standard error, standard out logs that the job is spitting out when it's running. Spark 4.0 introduced structured logging. Spark 3 does not. Not only that, but I'm sure in some of the Spark jobs that you've seen, people are doing random printf statements, debugging statements, and the logs that come out are not really structured, don't necessarily have timestamps on every log. So we couldn't just use standard log forwarding for a variety of different reasons. And then there's state tracking as well. So we're not using the operators, which kind of nicely put a CRD in the cluster that you can query to get the state of the Spark job. But in the Apache one, there's no TTL on it, so it just stays there forever. I think that bug might also be fixed too. But we needed a way to report our job status back up to our submission server. So let's see what we did here. For container logs, several options. This was a fun evaluation, particularly for me. I love logs. I even split logs in the woods sometimes, but a lot of different options. So for us, the requirements that we were looking at, we wanted it to be linkable from the Spark UI. The Spark UI generates these little links for the standard error and standard out logs. We wanted to make sure it was accessible at an HTTP endpoint somewhere. We wanted low latency, just on the order of seconds, right? We don't need millisecond latency for the logs, but we wanted them to be uploaded every few seconds. We wanted to maintain the ordering. This was really important because of all those printf statements in there. And just for a sense of scale, we do about 90 terabytes of logs per week from our containers, just for the Spark containers. FluentBit is a very common solution for this. A lot of organizations use FluentBit for forwarding both the container logs and the event logs. It works really well. We looked at Vector a little bit because somebody else internally uses it. We have our own logging pipeline at Airbnb, but it's much better with structured logs, as it probably should be. And then we looked at OpenTelemetry as well. So we eventually ended up going with OpenTelemetry, partially because we already use this at Airbnb, especially for metrics collection. So we wanted to try to keep as few moving components as possible and not introduce too many variables. What this looks like, we're actually not doing it on the Damon set for some various reasons. We're doing a collector sidecar on each Spark driver and Spark executor. That's just forwarding the standard error, standard out logs to S3. The one change that we made with OTel, the S3 exporter, is we added the ability to add a UUID v7 timestamp. If you're not familiar with that, it's a time-sortable UUID. So even if the collector sidecar restarts or something like that, we can reconstitute the logs after the fact. So the way that FluentBit does this is it maintains some state and has an incrementing integer, so it makes it pretty easy. But that didn't quite exist in OTel without doing some funky processors in the middle and stuff like that. So we just added that patch. The other thing that we did to make a lot of this easier from the developer experience is we created a per cluster reverse proxy that people could access to access the Spark UI and the history server and the logs all in one place. So for the running Spark driver, if you hit that /UI endpoint, it looks up the pod, either based on the pod name or a selector label, and does a reverse proxy to the Spark driver running on that pod. So it makes it really easy. We have a stable endpoint for people to get to the Spark driver UI. However, once that Spark driver is done, that port doesn't exist anymore. That service doesn't exist anymore. So we have a really simple redirect built into the reverse proxy that says, OK, if the pod is gone, push me over to the SHS endpoint. That's the Spark history server endpoint, where I can view the completed job. This is one of the things I really don't like about a lot of Spark solutions is when the job is done and you refresh it and it's just gone. And you're like, where did my Spark UI? Oh, I got to go back to that thing and find it and go back and do all this kind of stuff. So we just did a redirect. Works really well. For logs, let's see, we have our Spark driver UI down there, pushes the event logs to S3. When those logs are linked from either of the UIs, it goes through this path. And we look up the job ID in S3. We kind of we concatenate all those logs back together in that reverse proxy and serve them to the end user as one file. It supports range headers. It supports start-end parameters. So if the user kind of wants to page through there, they can do that as well. So works pretty well, and pretty happy with it. The other thing that we did for that is, we customized the Spark history server as well. If you're familiar with the Spark history server, what it does is it just sits there and it looks at all the Spark jobs that you have and loads the application logs into, it's like a Bolt DB or something based backend. We didn't want the Spark history server sitting there scanning millions of application logs on end when people only come in and view maybe 5 or 10% of them, right? So we modified it to load them on demand. So when somebody comes in and loads the Spark history server for a job, we'll go and we'll find it. It's pretty fast, except for really, really large jobs. But it'll save us on S3 costs for sure. State tracking was a fun one. Like I mentioned, both the operators maintain custom resources in the Kubernetes cluster. So if we had used an operator, we could have pulled those custom resources to get the status of the Spark job, but we don't really want to pull the Kubernetes cluster that much either. So we implemented a basic reconciler that lives inside each Spark namespace. So when that Spark driver runs, we just sit there and monitor the state of the Spark driver and push that state back to our Spark submission service. So we essentially have real-time updates for the state of the Spark job. The other thing that we did is we used a finalizer on the driver pods. So with all the pods flowing through, we didn't want Kubernetes to garbage collect a driver pod unless we actually know the state of the driver, right? Once that driver pod is gone, we would have lost if that job was successful or not. So we had a finalizer to the driver pod. Once we have successfully sent up the state of the driver pod, we remove the finalizer and let Kubernetes automatically garbage collect that. Even that wasn't quite enough to reduce the number of pods in the etcd. So we actually ended up with a custom descheduler that continuously runs, and if there's any completed pods, it just garbage collects them automatically as well. So that was also fun. All right, cool. So it's gotten a little more complex now. Here's our infrastructure so far. We've got our new control plane. That's got a reverse proxy and log server there. We've got our workload namespace, of which there are many, where people can run their drivers and their executors. The drivers and executors have these logging collector sidecars. We've got Kelleborn in there. It's running on high throughput EBS GP3 volumes, and then we're writing logs to S3. The other thing to note, there's a new box up there as well, just called Portal. We did a lot of work enabling ease of use for our customers too. So we've got an internal portal where you can go and you can search for their job ID. Regardless of whether it ran in the old environment or the new environment, it shows up in that portal. They click the same links in that portal, and they can go to the Spark UI in both environments. So that's part of how we're doing this migration without really bothering the users too much. All right. Anything else there? I don't think so. Oh yeah, the other thing to mention, the other part of the way that we've been able to ramp up to that 40% or that 38% so far is we have a ramp and opt-in process. So we use Airflow behind the scenes, as you might expect, and we can opt in different DAGs in Airflow to the migration. So we can say, okay, all these DAGs that start with X, let's run them in Kubernetes. If they fail there, we'll just rerun them in the old environment. All our jobs are idempotent, so we don't have to worry about any sort of duplicate data or anything like that. So that's been one way that we've done this really easily without disrupting our users. We can just not silently opt them in. Obviously, we work with those teams to say, hey, we're going to opt you in, so they're at least aware of it. But it allows us to do this without any user or any customer interaction, which is really beneficial and makes the onboarding process easier. All right, let's see. So how does this all get deployed? Essentially, I'm not going to spend too much time on this, but we use Argo CD. We've got Spinnaker that triggers Argo CD. All our configs are stored in Git. We've got our Unicorn queues in there. We've got our Spark configs, our Kelleborn configs. So we're using a collection of open source charts and internal Helm charts. When we click Go on Spinnaker, Argo CD is using that app of apps pattern, deploying that to each individual cluster or all of the clusters if we want to, and then each individual namespace as well. So pretty easy for us to roll out. Last week, we spun up a new cluster, and it was, I think, 2 PRs maybe, because I forgot to add a file. So this works really well for us. It's been pretty smooth. I want to give thanks to our internal compute infrastructure team for putting together this platform that makes it easy to deploy, because I wouldn't have been able to do it without them. So kudos to that team. But where do we use AI, right? Couldn't get out of here without saying at least one AI thing. Mostly kidding. I do want to give a shout out to the Kubeflow Spark History Server, MCP server. Too many servers in that word. This is pretty awesome. They've just published it open source recently. I hooked this up to our Spark History Server, and it does a fantastic job of actually helping users debug and figure out where their jobs are breaking down and what's slow. Other things I didn't get to talk about today, scheduling. We did a thorough evaluation of Unicorn, Volcano, Q. Eventually chose Unicorn, as I mentioned. Monitoring, I've got some sweet Grafana dashboards that I look at every single day. And scaling etcd and IP addresses. We had to do a lot of work there, right? We bumped up the etcd limit to 16G. We scaled up the node size there. We had to scale our API server nodes as well, and we're pre-warming IP addresses. But maybe if my talk for KubeCon EU gets accepted, I'll talk more about that stuff. But otherwise, I just want to say thank you. And one more call out, if anybody here is making this journey, please feel free to reach out to me. I'd love to share other things we do. I would love to create a community for us to share this information back and forth in a more open way. So please reach out to me if you're going on this journey. Thank you.